Hi, my name is Joy, and I'm the lead developer of the process module in QSDsan. This is a two-part video demo on the process module. You're now watching part 1. To access this tutorial, you can go to QSDsan's Read a Docs page, go to Tutorials, and then click on Process. As usual, this is an interactive tutorial, so we encourage you to open an empty Jupyter notebook to follow along. You can also download the tutorial file directly from our GitHub page. Let's get started. Previous tutorial covered fundamental modules and classes like component, waste stream, and SAN units. The process module we'll talk about today provides convenient features to implement dynamic process models that can be incorporated into SAN unit. Part 1 of the tutorial will focus on introducing the major classes in the process module. Part 2, which is in a separate video, will cover how to use this module to implement a dynamic process model of your own. Okay, first step, as always, let's import QSDsan. Specifically, we're working with version 1.2.5. I would recommend you to pause this video and update your QSDsan package if you currently have an older version. If you use a QSDsan package cloned from GitHub, then you can simply pull the latest changes. There are 3 main classes in the process module, namely process, processes, and compiled processes. Process is used to model individual dynamic processes with user-defined stoichiometry and kinetics. Processes is simply a collection of multiple process instances. Compiled processes is a processes subclass, but it provides additional attributes of the collection. It is often used to implement models with multiple dynamic processes in parallel. We can directly access these classes by calling qs.className. And then we'll get the output QSDsan._process.process, for example, if we call it process. This means these classes are defined in the _process module. QSDsan also has a processes module. You can check that by calling qs.lowercase processes. It means that processes is a folder. And to see what can be directly imported from this folder, we can call qs.processes.dunderall. This list includes ASM1, ASM2D, ADM1, which are common processes models implemented as a subclass of compiled processes. There are also utility functions like create something components and diffused aeration, which is a subclass of process. To get a list of all the attributes that the processes module has, you can use the dir function. So if we use it with a set subtraction, we can see that besides the functions and subclasses we see above, there are also these attributes, and those with the double underscores on both sides are built-in Python attributes, and the ones with a single leading underscore are individual scripts in the folder. For example, ASM1 is a script in the processes folder, and it defines all the functions and subclasses related to the ASM1 model. So let's use ASM1 as an example to learn about the core classes and features. ASM1 is a mathematical model for the active sludge processes in wastewater treatment systems. It uses 13 components to characterize wastewater and active sludge composition, such as biomass, organic substrates, organic and inorganic nitrogens, dissolved oxygens, alkalinity, etc. ASM1 includes 8 transformation processes of the components, such as hydrolysis of organic substrates and growth and decay of biomass. The stoichiometry of each transformation process considers conservations of COD, nitrogen, and electric charges. So to work with ASM1 in QSDsan, we need to first have the corresponding set of components ready. Let's start by importing the related functions in subclass. From QSDsan.processes, import create ASM1 components and the ASM1 class. And we call the create ASM1 components, and we can see that it returns a compiled components object containing the 13 ASM1 specific components besides water. And by default, we've set the thermals with these components upon its creation. We can check that by calling qs.getThermal. See that this is consistent with the components that we get above. Then we can go ahead and create an instance of the ASM1 model. If we call ASM1.Dunder basis, we can see that it is a child class of compiled processes. And let's take a look at the ASM1 documentation. It seems like all the inputs have a default value, and we can just call the classes without specifying any arguments. Now we get the ASM1 object with 8 individual transformation processes. Now, let's use one of them to demonstrate the process class. We can access the first process here by calling ASM1.tuple and with a 0 as index. Alternatively, we can directly access it by its ID, namely ASM1.arrow growth hetero. Now let's take a look. The show method prints P1's defining characteristics, including stoichiometry, reference component, rate equation, parameters, and dynamic parameters. All of them are stored as P1's attributes, so we can directly retrieve these information by calling the attributes. For example, let's see P1.stoichiometry. This means to produce 1 unit of XPH, about 1.5 units of SS, and 0.5 units of SO, and certain amounts of SH, SNH, and SAlk are consumed. Note that this returns a dictionary of numerical values, but in the show methods above, we can see stoichiometry is stored symbolically. And we can see that XDH has a stoichiometric coefficient of 1. That's what makes it the reference component here. We can access the kinetic rate equation of the process by calling P1 dot rate equation. This returns an formula with both symbols and some numerical values. Essentially, the rate equation is also stored symbolically. We can access that by calling the private attribute. In this equation are just replaced by its value if we check the parameters set here. To evaluate the kinetic rate of this process, we still need to input component concentrations to this equation. Let's try that. Here I'm creating an 1D array of 15 elements and call it state. The first 14 elements corresponds to the concentrations of the component, and the last one is the volumetric flow rate. You may notice that the rate of this equation only depends on a select few concentrations, but we still provide concentrations of the entire component set here because it's convenient to use the same array for all individual processes. Now, let's try this. Just need to call rate equation and then input the state array we created above. This means that when all the component concentrations are 1, the process happens at a rate of about 0.15 per day. And this value will change if the kinetic parameters are given a different value. Let's try changing some of the parameter values and see what happens. For now, these are the parameter values, but set them to different values using a p1.setParameters method. H, KNH, KS, KLH here. So let's change some of them. We can set mu H to 6 instead of 4, KS to 8, YH to 0.8. And now ASM1.parameters, you'll see that these values change too. This is because ASM1.parameters and P1.parameters are essentially the same object. We can verify that calling parameters is ASM1.parameters, and that is true. So when we set parameters for P1, we're changing parameters for the entire ASM1 object. If you evaluate the kinetic rates with the same state again, we're getting a different value. Another important attribute for process is conserved for. And this means that no COD or charge or nitrogen is destroyed or produced in this process. We can verify that by calling P1.checkConservation. If nothing is returned, that means COD, charge, and nitrogen are perfectly conserved for this process. Otherwise, I'll raise a warning or an error. And here we're getting a warning, and by the message, we can tell that electric charge is not perfectly conserved. Here, it's only slightly imbalanced, and this is possible due to rounding error. But if this figure is substantial, then that probably indicates there's something inconsistent in some of the parameter settings or some of the component settings. Moving on to processes and compile processes. QS.compile processes under basis. C.compile processes is a child class of the processes class. We know that the ASM1 class is a subclass of compile processes, which makes the ASM1 object also an instance of compile processes. And we can verify that. So is there a way to decompile ASM1 to make it a processes object? The answer is yes. We just need to do qs.processes and then input ASM1.tuple. And now ASM1 becomes a processes object instead of ASM1 or compile processes. Let's see what difference compiling makes. First, let's call ASM1.renderDict. See that all it contains is the individual process objects. But if we compile it and check again, we can find the dictionary became much bigger, meaning it has a lot more attributes than before. For example, we have IDs of all the individual processes. We have size, index, components, parameters, and stoichiometry. The list just goes on. We can check out some of them. Take a look at ASM1.stoichiometry. Instead of a dictionary before, now it returns a data frame. And each row is a process, each column is a component. This is convenient because it's in a format consistent with the Peterson matrix, which is often used in these kind of kinetic models. ASM1.rate equations. Now all the rate equations are put in the data frame. If we call the rate function method again with the same state array, it returns an array of 8 elements. Each indicates the rate of a single process instead of a single value now. And if we multiply each row of the stoichiometric coefficients by the corresponding state array, kinetic array, and then add them up row-wise, it should give us the production rate of individual components. We can directly access this result by calling ASM1.production rates. To evaluate it at a given component concentration, we just need to call ASM1.production rates eval and then input the same state array indicating the concentrations. Now it outputs an array of the same length as the component set. This method is very convenient when we want to incorporate process models into the mass balance of a unit operation. That concludes the first part of this tutorial on the process module. To summarize, process, processes, and compile processes are the three core classes in the process module. And they include attributes like stoichiometry, rate equations, and parameters, and useful methods like production rates eval and check conservation. Part 2 of the tutorial will cover how to implement a simple bug kinetic model. Thank you for watching and see you in part 2.